Good evening, everyone. Live from the Babio Center, it's Circuits, E245. Good evening, everyone. I want to begin by thanking the SITTV crew. This would not be possible without them. Sean is our cameraman tonight, very able. I thank you, Sean, for giving up your evening to be here. There's Matthew and there's Jesse, and I'm sure there's a few other colleagues I do not know names to. I want to thank them all. So thank you, SITTV. All right. So we're in the fall semester 2017. My goal for tonight is to spend the next hour and a half, hour and 15 minutes going through 7 problems that are hopefully going to guide you in studying for our circuits final. So let's get started. This should be posted on the course website. Just want to erase this. We did this before as a marker check. This is posted on the course website. I decided to go over the spring 2014 final exam. So we have a final exam from the spring 2014. Now, I suspect the first thing you're going to want to do is to copy the circuits one by one. So this is the circuit for figure 1. I think I know what's coming. It looks like an amplifier problem. So I'll give you a moment to copy that. See, this is where we need the Stevens Symphony and the Stevens Band to write some original writing music to kind of fill in the dead space here. Are we okay? We're good? Okay. Is this the first review session, Sean, that's recorded in 4K? Wow. What a momentous event this is. My colleagues, I'll put up the figure again in a moment, but I'm hoping a circuit like this, you're starting out the test with confidence. Now that you have most of the circuit drawn, let's just take a peek and see. It says what we're asking for is to determine an expression for V out over Vs. Okay, so we want V out over Vs. Now, before we look at the solution, let's see if we can solve it by ourselves without looking at the solution. So it says to determine, we are required or requested to determine V out over Vs. All right, now, a couple of things come to mind for me here. If I, if I look at this, I could start on the left or the right. It's up to you. I prefer to start on the right, more or less with the answer. V out equals something, then I can work backwards. So I'm looking at this saying, okay, I got to get V out in terms of Vs. So I say, okay, let me start over here. And I'm hoping this is now shouting out at you. There's an REQ. Okay? So it's the product over the sum, as I'm hoping you all know. So let's call that REQ right. Okay. So I then say, okay, I think I can use voltage division to get V out. Now, on the exam, you would have to write out what REQ right is, but that's in the solutions. We're not going to worry about that now. It's product over sum. So we're going to see that this is REQ, let's just call it R for right, REQ right over, and then that's R4. REQ underscore right, is that okay? R for right? All right, good. And then we have R4 plus REQ right. That's the ratio. And then I multiply this by the applied voltage, which is A times V in. All right, I'm getting there. I now have V out in terms of V in. So I'm asked to get V out in terms of Vs. So I say, okay, where do I see any chance of relating Vs and V in? I think it's the left side. Okay, so I now jump to the left side of the circuit, and I say, okay, I have R2 and R3. Again, in parallel, I think we're talking REQ left. So this is going to be product over the sum. So now I say, okay, how can I now get V in terms of Vs? And I think it's very similar. V in is REQ left. Again, using voltage division, REQ left over R1 plus REQ left. So that's the ratio, and I multiply that by Vs. Now, I don't have to do the algebra on the board here. It's all written in the notes, which we're now going to look at. But before we look at the formal solution, I'm asked to get V out over Vs. So what I'm now going to do is take this second expression for V in, and I just plug it in up here. And now what I get is V out in terms of Vs. I have it. So this was the electrical engineering part. The rest is algebra. I'll now show you the algebra. How are we doing? Any questions? All right, good. Thanks for the feedback. So let's now pop over to the solutions. And let's see how we did. Okay, I just carried everything through. We did the V out over V in. So my colleagues, this is the first one here, V out over V in. All right, that's this top expression here. Now I say, okay, let's determine the second one. And I get V in over Vs. My colleagues, that would be my second equation. And what you now need to do is just substitute one into the other. And you should be all set. One way to think about it that makes it a little easy for me is that how do I get V out over Vs? It's V out over V in times V in over Vs. And we have both of those terms. So just write it out, and we're done. That's part A of the problem. I think we're off to a good start. Can I help anyone? Okay. So, oh, yes, thank you. Yes, Vincent.
Would you be able to read the problem in terms of REQ and like write a key on the side?
I think so, unless I get possessed and say don't do that. So unless I tell you not to, assume you can, just define all the REQs. Fair? Okay, good. All right, good. All right. Now, this is a multiple part question. Okay. Second part of the question. The input resistance is defined as V in over I in. Determine an expression for R in. So R in is V in over I in. Determine an expression for this. So I think we need to go back and look at the figure. And I'd like to get an expression. What was I asking for? V in over I in? Okay. I see V in. I don't know about I in. How do I? Yeah, how do I relate the two? What do you think? What do you think, my colleagues? My colleague in the back. Vs over R1. The problem with that, my colleague, is Vs is not just over R1. Vs is over R1 plus this combination here. Here, let me show you how I did it. Thank you, though, sir. Thank you. Let me show you how I did it. And let's see if it makes sense. So we need V in over I in. So I just draw the left side of the circuit, and once again we have an REQ. Okay, so now I can think about reducing it to basically just two resistors. So we then have that V in equals I in times REQ. Now let me stop. That's the key. How can I help? Excellent. The question is a very good one. How do I know before I start solving part B that I did not need the right side? And the answer is the two variables that I'm asked to find are both on the left. I'm asked to get V in over I in. Both are defined on the left. Now, compare that to part A, where I was asked to get V out over Vs. They were both on different sides. Did I do okay? Great. So what we now have, my colleagues, is V in equals, now notice, I in is going to divide. Part of it goes through R2, part of it goes through R3. So by combining R2 and R3, we get an REQ. So I think now that's just one resistor. So V in, using Ohm's law, is I in times REQ. So I'm asked to get the ratio, and I think we're all set. It becomes just REQ. So R in is REQ, and that's the second part of the problem. How we doing? Sir? Oh. It's all right. I think I used to write REQ. But then I heard it was cool to say REQ, so I just started saying REQ. So you'll notice my progression over the years. Back then, I used to call it REQ, which it's not as nice as REQ, right? All right. So the question was, what is all this next to REQ? It's UIV. Okay. All right. Good. Are we okay on all of this? Part B is done. All right. Now, we're now combining a Thevenin problem with an amplifier problem, but you've seen this before. And I know I've met so many of you coming to my office about Thevenin, so I think you should all be able to shine here.
Wait, can we go back for a quick second?
Sure.
If we couldn't go over R1, why couldn't we go over the combination of just that part?
Okay, good. I have a question, but I'm going to need your help again.
So you said we couldn't just go over R1, but how come when we found like the REQ, we could just go over that?
Oh, the question is, I said we just couldn't go over R1, but how come we could go over REQ? The comment before was I in is Vs over R1. That's wrong. Because if you take a walk, you get minus Vs plus I1 times I in times R1 plus REQ times I1. Now, your question is, how come now we can just take the voltage across the REQ? Because what we're looking for is V in. So V in is defined to be across, depending how you read it, R2 or R3. They're both in parallel, so they have the same voltage. Did I do okay? All right, good. All right, I'm enjoying your questions. All right, now the next part is a Thevenin problem. My colleagues, I hope you know it's Thevenin. Just from the way it's worded, we have a load resistance. You want to select the load resistance to have maximum power. Those are the key words. Determine an expression for the load resistance to have maximum power. My colleagues, as you're writing that down, I'll erase this on the board here. This eraser isn't very good. Okay. So my colleagues, the whole point behind Thevenin is we're able to replace a complex circuit with a very simple circuit if all we want to do is connect to that circuit. So if I want to just connect to it, I can think of this complex circuit here as nothing more than a voltage source in series with a resistor. And what this question is asking is, you're now going to turn to this amplifier and add an R load. And the R load, we'd like it to be chosen so we get maximum power from the amplifier. So it turns out, it's proved in the book, the only value of resistance that will give you maximum power transferred is R load equals R Thevenin. So we say, okay, R load equals R Thevenin. And how do I get R Thevenin? It turns out that's V open circuit divided by I short circuit. So that's the little short lecture behind this problem. Now let's apply this theory to solve the problem. So I now go and say, okay, V open circuit is V out. Now before you write this down, let me go back and just show you that. We already calculated this in part A. V open circuit is V out. So let me go back and show you that. I'm going to pop open the circuit figure here. See, on the extreme right, notice we have, let me stand on this side so I'm not in the shade. I'm not casting a shade. This is A and B. So this is where we're going to put the load resistor. So V out here is V open circuit. And we calculated that in part A. So I'm good on that. Now, my colleagues, help me out. You should all know this, so I'm counting on you. Just by looking at it, what's I short circuit? Right? So we're going to put a short circuit here. And Dominic from Wayne, help me out. What would you say, my good man?
AVN over R4.
Perfect. AVN over R4. Excellent. You nailed it. If I put a short circuit here, remember in our lecture, I said you have to solve this problem twice? Solving it twice means I now have to forget about V out or V open circuit because I'm now going to put a short circuit here. Completely changes the circuit. So now the current goes through R4 and says, I'm not going through R5. I'm not going through R6. There's a short circuit in parallel with both of them. So all the current follows the outer path here. So what we have is I short circuit, using Ohm's law, V over R, is AV in over R4. Dominic, thank you for the assist. Okay. So my colleagues, I now go here. We already got the V out, and the I short circuit is AV in over R4. And R load equals R Thevenin for maximum power. And my colleagues, the rest is algebra. I'll have you look at that on your own, but we're just taking the ratio. And that's the value of our load for maximum power. How are we doing? Very thoughtful faces here tonight. Getting some thumbs up. Sam, help me out. I sense a question. I could be wrong.
Yeah. Can you just scroll up? Because where you get you have the V out, and then you times it by AVN, and then divide the whole thing by AVN over R4.
Help me out. I might not be following. Let me slide up. Sam, help me out. So the V out.
Is V out. Got it.
Got.
Yeah.
We're good?
Yeah, I had the wrong equation for V out. I wrote it down.
All right, good. All right? Okay. Yes, how may I help?
How can we just assume that the open circuit is equal to V out?
We're not assuming. We're told, although it's not written down, that V out equals V open circuit. Let me see if I can prove that to you. So we're not assuming that V out equals V open circuit. We are actually told in the problem, in the drawing itself. I lost my cursor again. There we go. Okay, see, it says in the problem, we're going to put a load resistor between A and B. So that's the extreme right. Okay, so then it says, you know, what's the resistance for maximum power? So basically it's saying the point of connection is between A and B. So think of putting all this in a box, and now we want to get the open circuit voltage. By definition, this is the open circuit voltage. There's nothing here but an open gap. And we have, in part A, that was what we called V out. Well, we got it for free. V out is V open circuit. Did I do okay? All right, great. All right. I think this is so much fun. What else would I be doing on a Wednesday night? All right. That's it. We're up to problem 2. Okay. All right, now, let me get problem 2 opened. Oh, this has the look and feel of a first order system, baby. Now we're talking, all right? This is like too much fun. You know, the only problem with me driving home, you know, they say after you take some medication, you're not supposed to operate heavy machinery or drive a car. You know, that's like me. I don't know if I can drive home after this. It's just too much. I'm just, you know, I'm in the left lane going 80 miles an hour. It's not good. It's not good. Justine, if I give a shout out to your aunt, would she watch this? Would you give her like a 30-second clip of this? You would? What's her name?
Cynthia.
Ah. Lawyer Cynthia. Aunt of Justine. Merry Christmas, Happy New Year, Happy Holidays from the Stevens family. How's that, all right? We did good? All right, my colleagues, I'm expecting to read a problem now where the switch is open, the switch is closed, we got T equals 0 plus, T equals 0 minus, what's this, what's that, Ke to the minus T over tau, blah, 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 blah. Okay, that's what I think is going to come. So we got this circuit, we got it drawn down, and now we're going to take a look at what we're asked. All right, now, just make sure you take your time and read it carefully. You know, so I don't want any problems on the final. Take your time. Know which side the switches are on and which is closing and which is opening. So it says here, the input source, voltage source, and the input current source are each a constant DC source. Now, I tell you, the circuit has been operating a long time. That's my way of telling you. As it is right now, it's in steady state. Okay, that's my way of telling you it's in a steady state. Steady state means, and I hope you know this, capacitors are open and inductors are shorts. All right, short circuits. So you are to solve for the capacitor voltage. All right, so we're going for capacitor voltage for t greater than 0. So step A, write the first order differential equation for the capacitor voltage for t greater than 0. Help me out. Are you going to use nodal or mesh if I'm asking you for voltage? What's your first instinct? Nodal. Very good. Very good. Force is strong with you, young Jedi Knight. All right? So we go with nodal. So instead of just looking at the answer, why don't we at least write the equation? We'll let the algebra go for the answers. We'll, we can, or I do all the algebra in the posted solutions. All right. So I want to solve this. Make sure I do this right now. I want to solve this for t greater than 0. So for t greater than 0, I think since this switch is open, but it's indicating it closes at exactly t equals 0, this switch is closed. And since this switch is indicated that it's going to open at exactly t equals 0, this switch is open for t greater than 0. So I think that I can ignore the right side of this circuit. And what I have is one resistor, R1, then R2 and R3, and then the capacitor. Now, if you get this wrong, everything else is wrong. You're going to be like, ah! So take a moment. Does everybody see that? All right. So what I now, and I bet you I actually wrote this. Let me, instead of me drawing it on the board. Aha. Good. My colleagues, I find it helpful to take a moment or two to draw it. Okay? Now, as I mentioned in another course I have, listen, this is our last 4 hours together. Don't have an Uber outside waiting to pick you up and running out in an hour and a half. Look, an extra 30 seconds to draw the circuit could make the difference whether you get the right answer or not. And it's not because you don't know how to do it. It's that you quickly read it and you made a simple mistake and it cost you 10 points on the final. You don't want that. So relax. 4 hours. You might not need it, but don't plan anything before 5 o'clock. Right? Or no, 12 o'clock. We have the 8 o'clock final. I got to leave at 5:30 to get here by 7:30. I got to be up at 4. I'm probably not going to sleep. I'll be with you. Listen, you pull an all-nighter. I'm right with you. Right? All right? So, my colleagues, I'm hoping you can write the nodal equation for this. All right? So, let me see if we can do it. First of all, this is V sub c of t. And that means, see how I drew this? This is all one node. Right? Because I can slide my finger along and there's nothing there but wire. So this is all one node and I say, I got it. So let's write this together instead of just looking at the answer. I'm in the node, current flows out. That's my assumption. So I'm looking at V sub c of t minus Vs. Exactly, you're helping me out. Over R1. Perfect. Okay. Next, V sub c of t over R2 plus V sub c of t over R3. And now I need the current through the capacitor. That's easy. We chant. I equals C dV dt. By the way, my colleagues, I'm not going to say who this person is because they're very humble. But someone did artwork, and it's on my door. And they have a drawing of me. I think it's very well done. They have me saying, in the node, let's take a walk, and then we chant. I think it's great. So I have it up. I'm going to try and get a frame for it and keep it longer. But that colleague also signed their name, so I'm very honored. When they become a famous artiste, I'll be like, that's it, I can retire. I got an original. All right. So, my colleagues, I'm hoping you can all do this. Are we good? Now, that's it for the electrical engineering. The rest is math. In fact, the rest is algebra. Okay? All you got to do is now put this into standard form. I'll leave you, look, you can do this. I know you can. Okay. You combine everything. I get it to look like this. And you know standard form. You know standard form. Standard form is when I have a 1 in front of the non-derivative. How can I help? I think the answer is yes, but please check me. The posted finals have the formula sheets. I think what I do is just give you the formula sheets for exams 1, 2, and 3, or 2 and 3, because we didn't have 1 for 1. So I think the answer to your question is yes. But please just double check me on the posted. So my colleagues, I now say I got this, and I know what's coming on the next page. There's probably 3 questions, B, C, and D. I know what they are. I know what they are. All right? So without even looking, first of all, are we all good on this? It's just algebra once you wrote that equation. We're all good? We're all good. All right, now, what's the time constant? All right? What's ever in front of the first derivative when we have it in standard form is the time constant. Now, I bet you the next question on the next page is what's the homogeneous solution? What's that? Ke to the minus T over tau. What's the particular solution? Right side if in standard form, if it's in standard form and we have a DC input. So I'm betting those are the next 3 questions. Yes, look at this. 5 or 6 points as a gift. Tau, homogeneous solution, and the particular solution. 6 points. Boom, boom, boom. Easy. We're good? I sense a question from my colleague. We're good? We're good. She's good? We're good? Okay. Absolutely. Let me know if you need me to scroll down. Yes, how can I help? The answer is no. The question is, are there going to be different versions of the exam? No. We're going to have one version of the final. So there'll be no difference. There's only going to be one version. Now, as a little footnote, this kind of strikes terror into my heart. I have not yet solved this problem as of the time of this recording. I probably won't get a chance to solve it till Monday, 2 days before the exam, or maybe even the day before the exam. Guess how many rooms we have been assigned for the final? 14. I think it's 10 or 14. I think it's 14. And the registrar says we recommend, alternate seating, which is fine. So we have blank rows. So if you take 400 colleagues, it now becomes 800 seats. We have like half the campus. So I know you have lots of questions now that you know this. What exam room do I go to? And you know what the answer is? I don't know. So the ECE department is working on this because the first question is, how many proctors do we have? I mean, people who can physically sit in the room and hand out the exam and collect the exam. That's an unknown answer at this point. All right? So, but we're only going to have one version of the final. What room do you report to? How many rooms we're going to have? I'll get it to you. Thank you. Good. Yes?
What are the synonyms, like as t goes to infinity, or other ways you could rephrase C and D instead of like using homogeneous?
Wonderful. What can I do to kind of change the wording of C and D? So the homogeneous solution is the transient solution. Because if I look at its structure, Ke to the minus T over tau, if you let T go to infinity, this, because of the negative T in the exponent, goes to 0. So this answer, this part of the answer goes away. So by definition, it's the transient. Now, if you look at the one below it, there's a couple of ways I could ask you this. Mathematically, we call it the particular solution, but it's also the steady state because it doesn't go away. The other thing I could ask you is, what's the answer as t goes to infinity? Right? As t goes to infinity, the homogeneous goes away, and you're just left with that steady state. So those are three ways I can think of asking the last part. The other one, all I can think of now, is homogeneous or transient. Thank you. All right, good. Let's keep pushing on. We're doing good. We're doing good. All right, now, determine, I'm reading down here now, determine the complete solution, solve for all constants. Now, it turns out that we have one unknown constant, k, the ke to the minus t over tau. So I say, okay, what do I have to do here? What I want is v sub c at t equal 0 plus. Why? Because the equation that we just wrote, the homogeneous plus the particular, is defined for t greater than 0. So what I want is an initial condition at t equals 0 plus for v sub c of t. So that's what I want. Now, here is a beautiful thing you can do. At t equals 0 plus, the switches were just changed. So the capacitor is a capacitor. But if I could go back in time to t equals 0 minus, the capacitor was an open and the inductor was a short. Life was simple. Can I do that? Yes. Why? Because the voltage across the capacitor at t equals 0 plus is the voltage across the capacitor at t equals 0 minus. That's because we cannot have an instantaneous change in the voltage across the capacitor. And that's because of the chant, I equals c dv dt. If the voltage were to change instantly, like a cliff, the derivative is undefined, or you can think of it as an infinite slope. We're going to have something we don't know how to deal with. So it turns out that there is not an instantaneous change. So what we need to do is go back to the circuit, and even though we want something at t equals 0 plus, we look at the circuit at t equals 0 minus. That's beautiful. So at t equals 0 minus, I say, okay, this switch is still open. This switch is still closed because it opens at exactly 0. We're looking at 0 minus. So now I'm not looking at the right side of the circuit. The left side of the circuit. My right, your left, sorry. I'm not looking at the left side of the circuit. I'm looking at the right. But now there's something even more beautiful. That inductor is a short circuit because the problem says it's been this way for a long time. So I'm going to redraw this circuit in my solutions, where I'm going to see a current source, R5, R4, and just a wire up here. And correspondingly, this switch is closed. I now get to the capacitor. It's open circuit. Sean, help me out. Sean is asking about an inductor. Sean, it's analogous situation. Sean, I'm going to answer your question now. Sean says, what does or does not change in an inductor? Sean, here's how I remember it. I equals c dv dt. What doesn't change? The derivative. Right? So when I equals c dv dt, what doesn't change is the capacitor voltage. Now, go to the inductor chant. V equals L di dt. So for the same argument, the inductor current at t equals 0 plus equals the inductor current at t equals 0 minus. Sean, did I answer your question? Good, Sean, thanks. So my colleagues, I'm now going to redraw this circuit, looking at the right side, inductors are short, capacitors are open. My colleagues, I think I see this. You may or may not, but I want you to come with me and see this. We're looking for the voltage here, right? I have two resistors in parallel. I'm going to think of an REQ. This capacitor is open. So what we're going to do is we're going to replace these two resistors with an REQ. And now the current is going through the REQ, and the capacitor voltage is taken across the REQ. So I think the answer is going to be IS times REQ. Let's now look at that. Let's now look at that. Okay, so we point out that, as Sean and I were discussing, that the voltage across the capacitor cannot instantly change. And I wrote down here, it might be hard to read, but you'll see it in the solutions, L is a short circuit. Okay, in steady state, the inductor becomes a short circuit.
It's been steady state like this whole time, but when we were on the left side, the C wasn't open circuit, so why is it open circuit?
Excellent. Why was it open circuit now? Why is it open circuit now and it wasn't open circuit in part A? Excellent question. To help me answer it, I'd like to pull up the figure. So you are correct. What the problem says is the way the switches are now, they've been here for a long time. So that's telling me the way the switches are right now, capacitor is open, inductors are short. Now, so that got me to apply it in this part of the problem. Now, in part A, what happened? Part A, we're looking at t equals 0 plus. So we got to instantaneously close this switch and open this. Now, nothing has been there for a long time in terms of the steady state. So now we have to solve it. Did I do okay? It all has to do with the changing of the switches. All right. My colleagues, I'm loving your questions. All right, so we get an REQ, capacitors and open. We have an REQ, so this is important. I showed that I mentioned the capacitors and open. So the voltage across the capacitor is REQ times IS. And my colleagues, I think you're on your way. We then say, okay, what did we have from the first part of the problem? The voltage across the capacitor was Ke to the minus t over tau plus the right-hand side. And I say, okay, at t equals 0 plus, we just found out that it's REQ times IS. So I let t equal 0. I get Ke to the 0 plus the right-hand side. I solve for K, which I've done here. I get K, and then you just plug it back in, and you're done. All right. Besnick, how are we? All right, good. Good. All right, good. I'm looking around to see if there's any questions. All right, so the answer is here. All right, we're pushing on. Oh my goodness. Aren't finals great? There's a part F. We're like breaking records here. This is like awesome. We're up to part F. I wonder, are we ever going to make a Z? That would be like unbelievable. All right. All right. My colleagues, I say, look, before I tell you what I'd like you to solve for, let's see if we can make life a little easy, okay? And here's what I mean by easy. So, Justine, I don't know, this is like a crazy answer here. So, this is the answer. There's some constant times e to the minus t over tau plus another constant. That's what it comes down to. So it's some constant times e to the minus t over tau plus another constant. So what I ask you to do is, let's call, instead of having to write this out all the time, let's call them like K1 and K2 or something like that, make life a little easier. So I start the next part of the problem by saying, define the constant in the homogeneous solution to be K. Okay, just have to write it as K. And define the particular solution as K1. So now what we have, that crazy answer we just wrote, is now K e to the minus t over tau plus K1. So we keep it nice and simple. Okay. I then say, tell me the time it will take for the capacitor voltage to reach X% of its final value. I like this. How long will it take to reach 80%, 85%, 90%? So how long will it take to reach X% of the final value? Now, you know what the hardest part of the problem is? And I liked your question so much before because your question answered this. Here's the hardest part. What's the final value? Excellent, Sarita. K1. Because as you pointed out to me earlier, you let t go to infinity, e to the minus t over tau goes away. So, my colleagues, the final answer is K1. And now we want to get to X% of K1. So just have confidence in yourself. You can set this up. So the time to reach X% of the final value. The final value is K1. So X% of the final value is X over 100 times K1. So I want to determine the time it's going to take for the capacitor voltage to get to X over 100 times K1. For example, we typically, not always, we typically would choose X1, X or X1, X to be 90%. So how long does it take to get to 90% of the final answer? So this would then be 90 over 100, or 0.9 times K1. So now that becomes this side of the equation. X over 100 times K1 equals K e to the minus t over tau plus K1. Solve for t. That's it. Just solve for t. So it's just a little bit of algebra, not much. We take the natural log to get rid of the e, and that's how long it takes to reach X% of the final value. At this point, I think we're done with the second problem. We're doing good. Okay. Look at this. Took us almost an hour to do 2 problems. Oh boy, this is going to be a lot of fun. Okay. All right. Are we good so far on this? All right. Onward and upward to problem 3. Get the voltage V1. My colleagues, I think this is easy. I really think you can get this. All right. This is chapter 5. I think we just had it. We had it on exam 2, but we had a little bit of it again on exam 3 with the power problem. So I look at this and say, okay, this is going to be getting the steady state voltage V1, and I'm hoping you're sitting there saying this is nodal and this is complex arithmetic. And if that's what you're saying, you got it. Let's just write the equation together. So where am I? Where I hang out. I'm in the node. All right? I'm in the node, and I say, I got to write the nodal equation here. You can do this. So what I get is V1 minus 10 at an angle of minus 45 degrees divided by 10 ohms. Now let me stop. This reminds me very much, I think, of our both of them. The second problem where we had to write nodal for the capacitor. It's very similar. So I'm in the node, so I assume I'm at the highest point. So it's V1 minus Vs, which is 10 at an angle of minus 45, over 10. Plus, just keep going. V1 over 10 minus J10 plus V1 over 10 plus J10. And now, how do I handle that current, my colleagues? Sir? Right. Positive, negative? Why negative, good sir? Because it's going in, and our reference direction is out is positive, so we're going to say you're coming in, it's negative. So it's minus 5 at an angle of 45 degrees, if I've done all this right. And this all equals 0. So let me pop up the solutions here. Okay. Now, to me, the first equation is key. V1 minus 10 angle minus 45, 10 plus V1 over 10 minus 10. Okay, I think we did it. Now, my colleagues, if you don't mind, I'm leaving the rest to you. I know you can do it. The rest is complex arithmetic. We've done it a few times. The exam, homework. I have a practice problem posted on the website from chapter 5. So my colleagues, I think you can do this with enough practice. So this is problem 3. And now we're going to do problem 4. And I think problem 4 is near and dear to your heart because it's real and reactive power. And I bet you know how to do this too. So here I give you everything in terms of the V1, and now I'm going to ask you for the real power and reactive power of different pieces. How are you on this? Let me see if I can begin and make sure we're all okay, and I welcome questions. So I don't get confused while you're drawing that, let me erase this. God bless. All right, I think you've had enough time, I think, to draw it. I'll give it another moment or two. I see some colleagues still writing. All right, I think you had enough time, I think, and let's now go and see what we're asked to calculate. Okay, determine the reactive power for the capacitor. All right, determine the reactive power for the capacitor. So let me go back and look at the circuit. So the capacitor is minus J25. Now, my colleagues, some of you may like to do voltage division. Others may like to just figure out the current and take it from there. Whichever way you're more comfortable with, you're going to get the same answer if you do it right. So here's what I do, but you can do it the other way. I want the power for this capacitor. So what I remember, and my colleague, this is on the formula sheet. What I remember was P equals V squared over R and P equals I squared R. Well, it's very, very similar here. The reactive power Q is I squared R, in a sense. It's IRMS squared times the reactance. And the reactance here is the reactance of the capacitor. Now, you don't have to memorize this formula. It's on the formula sheet, but there you have it. It's I squared R, very similar. IRMS squared times the reactance of the capacitance. So, my colleagues, I'd like to get I. So, I is going to be V1 divided by Z, where Z is the impedance of this here. My colleagues, if this was a Chapter 2 problem, and I asked you for the current, and this was R1 and R2, I'm hoping you would say, oh, that's just V1 divided by the sum, R1 plus R2. Same thing here. So I1 is going to be V1, which is 7.14 at an angle of 45 degrees, divided by, now what's the Z? 25 minus J25. I think the lights are going in and out. If the lights go out, don't worry. I have a switch. I'll try and put them back on. I think the building is on timers sometimes, and it must be 10 o'clock or maybe 10:15. I guess they might be thinking it's time for us to leave. The original question has multiple parts. The first part that we're looking at is to determine the reactive power to the capacitor. So my colleagues, I can now figure out I, and once I get I just take the RMS value of it, square it, and multiply it by minus 25. We drop the J, but we take the negative sign. So all of that is now shown here. Okay. So determine the current through the capacitor, and we get this value here. Now remember, my colleagues, I hope you all know this. How do you get RMS? Divided by the square root of 2. Okay. So we get the square root of 2 in there. We square the whole quantity. When you take the reactance, you leave the J, but you take the negative sign. So it becomes negative. So reactive power to a capacitor is negative. Reactive power to an inductor would be positive. My colleagues, did I do it the alternate way? Yeah. If some of you would like to have done it by using voltage division, you'll get the same answer, and I've done it here by voltage division. So whichever way you want to do it, you should be good. How are we on part A of this? Okay. All right. So we just continue on. Now I ask part B, determine the reactive power for the inductor. It's the same approach. Let me just go back and look at the circuit. So I say, how am I going to get the reactive power to the inductor? Again, it's going to be V1 divided by 25 plus J25. That gives me the current. And then I just take IRMS squared times plus 25. If you prefer voltage division, you can do that way also. So this is now part B. And alternate approach is voltage division. How are we doing on real and reactive power? I think I get the feeling you're really solid on this. Okay. The last is determine the real power delivered by the source. What would be helpful here is if I could figure out the current I. So notice I didn't draw the whole circuit. This is meant to be like dotted lines, but it's Vs and R, and that's V1. So my colleagues, if I think of I as flowing in this direction, the current through the source, I say, oh, okay, how do I get I? I is going to be 10 at an angle of 45 minus V1 over 10. And just go ahead and solve for I. And again, this is in the formula sheet. Is this real power? Real power delivered by the source is VRMS, IRMS, cosine theta. Okay? So I say, all right, just remind me of that. Now we calculate I. And then we have I is here. Now, by the way, I'm using this formula because I know V and I know I. So I got it. So it's VRMS, IRMS. Again, square root of 2, square root of 2. And what you might forget, because we haven't done it enough perhaps, is what's theta. Okay? It's on the formula sheet, the angle of the voltage minus the angle of the current. So turns out here that the current is 45 degrees. Has an angle of 45 degrees, pardon me, and the angle of the voltage was also 45 degrees. Okay. They're trying to send us home. It's like when you're at a club late at night, they turn the lights off. Get out of here. Sam, give me just 1 second. Hold on to your question if you don't mind. My colleagues, I think there's a button back here. Are we, Sean, are we back to, we're still good on the light? It's a little dark. It was? So if it goes out again, it's okay? Should I turn them off? Okay. I might keep it the way it is because I'm afraid if I start touching buttons, I don't know what's going to happen. Sam, I'm sorry to hold you on wait.
I'm confused how you found the current in this one.
Good. The question is, how did I find the current? So, Sam, I didn't mean to do this on the exam to be devious. But on our exam, I specifically wrote for exam 3 this semester, the current was this way. I didn't do that here, just probably because I thought everyone would know that. So we look at this problem and say, this is the current direction I. Now, how do I get it? This voltage minus that voltage over 10. Sam, did I get your? All right, no worries, Sam. I hear a voice. I hear a voice. Sam, so we're good? We're good. Sarita.
So that means that we're always going to have a resistor in series with the voltage source.
Oh, I never said that.
But like, then how would you get the current there?
Oh, remember, if you had a capacitor, Sarita, this is an AC circuit. The capacitor is charging and discharging. It's not a DC circuit, which I think you might be thinking, and forgive me if I'm wrong. If I had a DC source with a capacitor, that capacitor would block the DC. You're right. But this is an AC circuit. We're charging the capacitor, then it discharges when the sine wave or the cosine wave becomes negative. So I hopefully have never said whenever we have a voltage source, we always have a resistor. I mean, that's not a bad thing, but I could have replaced that, or what I could have done, Sarita, is I could have added a capacitor in series with it.
But there's always something there.
There's always something here?
So we can get the current.
That was a question. Right. At the very minimum, there's a wire here. Now, if there was a wire here, then what's the value of V1? Vs. Changes the whole circuit. Right? Am I getting your contribution? Am I? No, I get confused all the time too. Don't worry. So, Sarita, this is a very practical circuit because we can argue, and we're right, that a voltage source has internal resistance. So you often show it as a ideal voltage source with a resistance. Your car battery has internal resistance. And if you don't start your car for X number of months, the battery's dead. And you say, well, how did that happen? There was an internal discharge, so we model it as our internal resistor. So this is a very nice and valid model, but could I change it? Absolutely. I could put a capacitor here and a whole bit. Sarita, we're good? Oh, awesome, good. We need anything else? We're all set on this? Sir, how can I help?
Just to be safe, reactive power can be bars or watts, correct?
Right, let me repeat what you said because you're 100% right. Reactive power can be watts or VARs, volt, amperes, reactive. You use either one, you'll get... Real can only be watts, exactly. Are we good? All right. I think we're done with problem 5. No, problem 4, pardon me. All right. So I'm thinking the first 4 problems were fairly friendly. I'm allowed to just a little bit, just, you know?
See what we put on the paper.
Exactly. No, I never laugh. I never laugh. So, let's look at the circuit first. Dun, dun, dun. Story you're about to see is true. Oh, this looks like a filter. I'm thinking filter here. I don't know. I could be wrong. Now, I remember on exam 3, depending which version you had, it was just an R and an L. Who's this professor think that they're allowed to put in an extra R? Who? Who told him he could do this? All right? So we go from an RL to now a slightly, just a little bit of a curve, just on the outside corner of the plate, just painting that outside corner. Can you hit the outside pitch, all right? So now we got an R and an L and an R. Just a little bit, Sam, just a little, all right? So I say, all right, here we go, baby. What do you got? Derive an expression for the transfer function of the filter. You do not have to put it into standard form. Oh, that's good. You know what that means? Standard form is too hard to get it into standard form. So we don't even have to get it into standard form. Here's the term you have to get it into. J something over something plus J something. That's what we want. All right? So Vincent, we're going to be able to figure this out. So I'm sitting here in the exam, and I'm thinking, all right, if it wasn't for that second resistor, I would use voltage division. So I'm thinking maybe even with that second resistor, I should use voltage division. So now, we don't have an REQ. We have a ZEQ. Okay? Exactly. We got a ZEQ. The ZEQ, because I got an L and an R in parallel. So I say, wait a minute. Oh, no, tell you what, I just saw faces. See, this is not good teaching. See, let's take it one at a time. Okay? How do I get ZEQ? Product over sum. What is the resistance of reactance? What's the reactance of an inductor? J omega L, J 2 pi FL. So product over sum, R times J 2 pi FL over R plus J 2 pi FL. So I just rewrite this, and I say that is ZEQ. So my colleagues, instead of having the R and the L in parallel, I now replace it with this, which is the ZEQ. I now do voltage division. Same thing, ZEQ over ZEQ plus R1 times Vn. And we got it. All right, so my colleagues, let me show you the drawing again, just so you are okay with this. This now becomes ZEQ. So how do I get V out? ZEQ over R1 plus ZEQ times V in. Just want to get back. And my colleagues, there we have it. Now, I don't like the kind of like the multiple divisions here in the numerator and the denominator. So I think what's nice, I think what I do here is just multiply everything by R plus J 2 pi FL. I think that makes life a little simpler. I now multiply, and I get this here, multiplying by R plus J 2 pi FL. And my colleagues, a little bit of algebra, and we got it. We now wrote it in the form of J 2 pi FL R2 over some constant plus J times another constant. That's what I asked, and you did it. Now, my colleagues, let me go over this again. I know you're all taking very careful notes. First step, determine ZEQ. Second step, voltage division. Third step, just two lines of algebra. I guess if you want to count the last line. 3 lines of algebra, and you got V out over V in. How do we do? How may I help?
So, when I saw like the scroll up.
I'll scroll up, be happy to. Right, so for the first V out over V in, I think you mean this here.
Yeah. So, when I saw that, I thought that was the final answer.
Right, one might think that.
Because you could just pull out the J and then it's a term.
Yeah, but help me out. You could have a good argument here. Let me go back and read what I wrote. I asked for J times something over another term with no J plus J times a third term. I think you will have a hard time pulling out the J. I think. This would pose some problem for me how to pull out the J here.
Well, no, if you just take the J out of the numerator.
Oh, but then there's a J here, though. My question may not have been clear. It was the J outside of a term that has no J in it. I see your point, though. You're absolutely right.
Okay, so if you would have done that on the test, would it still be like?
Yeah, I work. The question is, you know, here's what would have happened. you would have been fair in your reading and interpretation of the problem. Unfortunately, points would have been deducted, all right, because I didn't see your point of view. So the grades are entered. I disappear for Christmas. I'm deep underground, hiding. No one knows where I am. I don't answer emails. I come up for air on January 10th. I get an email from you saying, wait, I thought I did a lot better on the final. So I say, I have your final. Come in and show me. And we can always do a change of grade, as long as it's done, you know, expeditiously in the start of the new semester. So I don't want you to worry. I try to make the answer key as clear and as, you know, but I'm not, so you can come and see me and we would work it out. Sounds good? Yeah. All right. My colleagues, that then takes care of this, and now we got the answer. So far, so good? All right, now, for R1 and R2 is 10K, and L is 1 millihenry, and you're given this input, figure out V out. So, my colleagues are hanging in there. By the way, to the studio audience, you are not required to stay till all 7 problems are done. So if you have to leave, I totally understand. I won't take it personal. All right? So now, the key theory here is that the transfer function, which is what we have just derived, is V out over V in. So V out becomes V in times the transfer function. So I say, all right, what is V in? I have to write V in phasor form because that's the math I'm going to use. So V in is 100 at an angle of 30 degrees. And now I substitute 10 ohms and 1 millihenry. How did I get the frequency was 100 hertz? Sir? Right. Excellent. That was very good. The standard format is 2 pi ft. So 2 pi ft equals 200 pi t. As our colleague so accurately said, f is then half of 200. So f is 100. So I plug all this in to the transfer function. I'm just plugging everything in. Now, Sam, I'm thinking of you here, my colleague. I'm just plugging everything into this equation. So my colleagues, this was the answer to part A. I plug in the R and the L and the F, and it gets a little easier. All right? So I plug all this in, and I now get this. I work out the math, and I get H of F is this. Now, my colleagues, a filter changes 2 things: the amplitude and the phase. So I now need to get 2 equations, one for the amplitude, one for the phase. So I say, all right, how do I get amplitude? Think of the magnitude here. How do I get the magnitude of this? The magnitude means the length of the vector. That's what it means here. So I have a vector in the j direction. It's pointing straight up. And its length is 6.283. That's the magnitude. The bottom, I used the Pythagorean theorem. And I get the length of the vector to be 100 squared plus 12.566 squared square root. And I get H of F. How am I doing? All right, good. How do I get the phase angle? My colleagues, be careful. What's the phase angle of the numerator? 90. Excellent. Because the vector is in the j direction pointing straight up. So it's 90 degrees. How do I get the angle of the denominator? The arctan, right, of the opposite over the adjacent, which is here. So I get an angle of 82.84. I got it. This looked really complicated, but we're figuring it out. I now take h of f times v in. So that's the value for h of f. I now multiply it by v in, and I get v out. Now, my colleague was so helpful here. I wonder if I could call on you again, sir. You were so helpful before. How do I know the output frequency now? Right, so we had v in, and you were very helpful pointing out to me what the frequency of the input was. What we've now done is I've calculated the output magnitude and the output phase. How do I get the output frequency? Perfect, exactly, right? So the thing that doesn't change is the frequency. Good job, sir, thank you. What happens is we change the amplitude and we change the phase. The frequency doesn't. So just keep the frequency the same, and we say, okay, how do I convert this to a cosine? Easy, 6.23, and that's the angle, and we're done. And I think we solved a somewhat complicated problem. How we doing? Okay. All right. All right. Now, for this part of the problem, I know you're beginning to hate me, all these parts. You might say, gee, 6 problems didn't sound bad, but I didn't know we had like, you know, multiple parts per problem here. This is a little unfair, all right? So this is our circuit. However, I now tell you R2 is infinite. So R2 is infinite. So R2, open, gone. So now I say, all right, how do I get V out over V in? See, now I'm happy, because this is now the RL circuit that some of us might have had on exam 3. I now say, gee, I think I know how to solve this. So what do? I use voltage division. And I get j omega L over R1 plus j omega L times V in. And I say, oh, I know this. I think this is a high-pass filter. And I say, I think we can define the break frequency as 1 over 2 pi tau, which is 1 over 2 pi L over R. In this case, R is R1. And we now get H of F in standard form and the break frequency. Believe it or not, I think there's one last part. What do you think I ask you? I've asked just about everything. What? Good man. The Bodie plot. The Bodie plot. All right. We're good? All right. So we now have, the next one is the Bodie plot. My knees are getting to stiffen up here. All right. The Bodie plot. This is a high-pass filter. How do I know it's a high-pass filter? J over 1 plus J. J times F over FB over 1 plus JF over FB. It's high-pass. You could also figure it out if you looked at the role of the inductor. And I look at this and say, okay, it's a high-pass filter. And I now draw the Bodie plot. Notice, I would have taken off points on myself here. Look how sloppy I was back in 2014. What did I not include? Exactly. The 3 dB point. Forget it. This guy is out. This guy's the professor? I don't know. I would put a 3 dB point and asymptotically with the curves and the whole bit. All right. We're good? All right. Yes, how may I help? Right. Exactly. The low pass Bodie plot, right, would be flat out to the break and then goes down. And you would label the axes similar to what you've done here. Did I do all right? Thanks for the assist. All right, good. Last problem on this exam. Last problem. This was an exam. All right. So, this is one of my favorite parts of the course. We talked about digital signal processing. And Sean, I'm truly honored. Here we are discussing digitization and digital signal processing. And this is my first session filmed or recorded in 4K. Somehow I think there's a synergy here. This is wonderful. All right. So my colleagues, let's see how we do on these questions. In this problem, the A to D converter has a sampling rate of 44,100 samples a second. What's the highest allowable frequency that can go into this A to D converter? Now, here's where we have to remember what Harry Nyquist told us. Harry Nyquist said the sampling frequency has to be at least twice as high as the maximum frequency in the incoming signal. So I just asked you this question backwards. I told you the sampling frequency. What's the maximum frequency? Cut it in half. So 44,100. We get 22,050 is the highest frequency you really should put in here. Now, it says here that we represent each sample with 16 bits. That's a 16-bit A to D converter. Next part of the question, what's the number of bits generated in an 80-minute period? Okay. So here, follow the units. 44,100 samples per second times, how many bits again? 16, thank you. 16 bits per sample. So samples cancel. I'm left with bits per second. So what I now do is I multiply by 80 minutes. That's what I asked for, right? 80 minutes. I just got to convert minutes and seconds here. So I'm going to have 60 seconds divided by 1 minute. So the minutes cancel, the seconds cancel, and that's the answer. Huge number. We're good? We're coming down the home stretch. Can I be of any help? I sense there's a good question. Can I help, sir? Or you're okay? You sure? All right. A recursive equation for Christmas. All right. So now we have a recursive equation here, and we're going to solve this. We're going to figure this out. It says the digital computer implements the following equation. Now, this is the equation for a particular filter. So this is how we're building the filter. And let me just write the equation down. My colleagues, I don't want this to stress you out. When you get to this point of the exam, solve it one step at a time, and you should begin to see some kind of pattern or some general way to write down the final answer. All right. A is a constant, so I'm going to leave A as A. And the input, notice, the input is 0 everywhere except at n equals 0. And we're told that the initial condition for y is 0. For n less than 0, y is 0. So that tells me I start at n equals 0. So I ask you to solve for y sub n. My colleagues, take a deep breath and relax. You can do this. N equals 0. This becomes y of 0 equals a times y of 0 minus 1. That's minus 1. Plus 1 minus a times x of 0. Now, y of minus 1. Wait a minute. You just told me y for all values of n less than 0 is 0. So this whole thing is 0. So y of 0 equals 1 minus a. And I say, wait a minute. What's the value of x at 0? 1. So I just say, okay, it's times 1. Now, my colleagues, solve it for n equal 1. So go back here. Y of 1 equals a times y of 1 minus 1, that's 0, plus 1 minus a times x of 1. Now, x of 1, I say, wait. For n greater than 0, x of n is 0. So this is 0. This right here, that's 0. So what I get is y1 equals a times, now y0. What's y0? 1 minus a. Do it a couple of more times. I've worked it all out here, step by step. If you did it for n equal 2, you would get a squared times 1 minus a. The pattern is a to the n times 1 minus a. So I wrote that up on the top. I wrote it down here. A to the n times 1 minus a is the answer. We got one more quick question to go, and then we're done. But that was this complete exam. But they didn't get into Chapter 7. We did. Extra credit, I know. If you read enough of these extra credit questions, you probably figure out most of my life. The first car, my favorite dog, my favorite TV show. All right. Okay. Are we good? We got one last question to go on a separate exam that deals with Chapter 7. How may I be of help? I'm sorry? Why? Have you seen this equation before? Oh, this was the same problem as in class? Oh, the equation might be the same, but the input was different. Okay, so your question is, am I always going to give you the same equation for y? No. I might not. You're very observant. I don't even think I noticed that. You're very observant. All right, good. Anything else? All right, 5 more minutes and we're done. Now, what I'm about to discuss, we in the home audience, you will have seen if you've come to class on Thursday. But this is being recorded Wednesday evening. So my colleagues here this evening, we haven't exactly covered this in lecture. So let me go over it now quickly. And you're going to come to lecture tomorrow. You're going to say, I get it. It's perfect. I understand it. So I got to show you a table first. Now, where is this from? Fall 2013. This is fall 2013. Fall 2013. Now, before you say, what the heck is going on here, let me show you the associated information. Why? Why the moaning and groaning? This is circuits. There's no moaning and groaning. We're happy. We're happy electrical engineers. All right. So, here's what I tell you. Now, again, I don't want you to leave here discouraged tonight because we haven't gone through this yet, but we're going through it now. So, you're definitely going to leave here tonight, I think, knowing something you may not have known before. Some of you, again, may have had this somewhere else in your life. All right. So here's what I ask you to do. Here is your digital circuit. Here's your requirements. You have 3 inputs, A, B, and C. Now, think of it as turning on the light or something more exciting like the robot moving or an alarm sounding. And you say, okay, this is A, B, C. I want the output D to follow this. I want the output D to follow this. So I want to build a circuit. Now, there are 2 ways of doing this, as you'll see in tomorrow's lecture. Product of sums and sums of products. Very good. You've had this before, young Jedi Knight. All right. Product of sums and sums of product. Okay. So, here's what we need to do. We go back and we say, okay, using the sum of products approach, write the expression, the Boolean expression. Now, my colleagues, I claim once you write the expression, the design is easy. Right? This is an AND gate with 2 inverters, not A, not B, and C. Okay? So this is the key. So I say, how'd you get that? Where did that come from? All right? So it's the product, excuse me, sum of product. Now, wait a minute. Does this make sense? Sum of products. I know those are ORs and these are ANDs, but it's a sum of products. So here's what you do. For the sum of products, you go to the truth table and you find all the D's that are 1. So for the sum of products, you go to the truth table and you find all the cases where D is 1. Now wait till you see this. You'll be like, is that it? Is that it? And I'll say, yes, that's it. You're done. Here we go. Wait till you see this. What a way to end our lecture. Now, my colleagues, how do I get the first 1 for D? I think it's not A, ANDed with not B, ANDed with C. Do you see that, my colleagues? Not A, not B, and C ANDed together would give me 1. Sir, that's it. Well, we got to do it for all ones, because then it becomes the, can you help me out? Can you maybe do the next couple? What do you think?
So the next one would be not A.
Perfect. Perfect, perfect. Keep going. You're doing good, sir. Perfect. All right. Now, that's, okay, good. That's the product. All right? And as you're pointing out, this is sum of products. So we just do this. Now, isn't that a cute way to do digital design? It's really nice, isn't it? So you use AND gates, inverters, and OR gates, and you've designed that logic box. Now, there's a second way. Let me just show you that, and we're done. We're going to wrap it up. Okay? Close down production. All right? Second way, let me just check, by the way. You can see my answer key. My answer key, come on, cursor. There it is. That should be what we've written on the board. Okay? Now, the second approach is product of sums. Okay? So product of sums. Now, this is the answer. Notice, we can think of it as a product of sums, the ANDing of ORs. So, my colleagues, if for sum of products, we went to the table where it was 1. The other case, which is the product of sums, we go to the case where the table is 0, the output is 0. That's it. All right. Now, my colleagues, using ORs, how would I get the first term to be 0? All right. So I say, wait a minute, I think I just saw that. That should just be A or B or C. A or B or C in the first row will give me 0. Go down to the next row. So what we have here then is A or B or C. Now, go to the next 0. Now, make sure I don't make a mistake. A or not B or C. A or not B or C. Where's the next one? Not A or B or C. All right. Make sure I'm not skipping one. 1, 2, 3. Then it's not A or B or not C. Not A or B or not C. Is that it then? Yeah, that's it, right? And what do I then do? AND them together. And we got it. It is. It's cool, isn't it? It's fun.
So, just like to simplify a little bit, thinking for product of sums, it's kind of like the opposite of what you see.
Oh, I don't know what you mean by that. Products of sums is the opposite of what you see. You got me there.
So going back to sum of products, when you see a 1, you say the letter. When you see a 0, it's not the letter. But then in sums, product of sums, it's, you see what I mean? Like it's,
Yeah.
because you're trying to match it with a 0.
That's it. You know, I feel comfortable saying it that way. I'm sure what you're saying is right, but I'm not following it, so it's my bad. It's not yours. So you're right. In product of sums, we want the parentheses to give us 0. My colleagues, I think this is one of my longest review sessions. Sir? Yeah, the question is, would I ask you to draw the circuit with the gates? I did that one year and people revolted. So, no, I figure if you could write the equation, you could figure out the logic gate. So to answer your question, I'm going to ask you for the expression not the circuit. Not going to ask you to draw the circuit. All right, it's time to wrap it up. Thank you, thank you, thank you. What a wonderful show. All right, that's it. We're all set. Thank you. All right. All right. 2 hours of circuits fun.